Hello, we're going to go over the third part of Chapter 9. This is going to cover sections 9.8 through 9.11, and we're going to talk about reactions 6 through 9. So we're going to start here with reaction number 6. In this reaction, we are using 1 mole of halogen and reacting it with our alkyne, and we're using CCl4, which is carbon tetrachloride, so it's just our solvent, it's not showing up in the reaction. And our halogen here can be either bromine or, and what we create is a halogen added to each of our alkyne carbons, and our triple bond is reduced down to just a double bond. Now this is a mixture of an anti and an addition. The major product is the anti-addition, or our halogens being trans to each other, and the minor product is the syn addition, or having our halogens cis to each other. Now it's really important that we equivalent. One way to write that is 1EQ, and it's important to write that because down here when we have excess halogen or 2 equivalents of halogen, we're going to add twice as much. So here's our alkyne, and again we're adding either chlorine or bromine to this, and we're going to add 2 halogens to each of our alkyne carbons, tetrahalide. So in our carbon here we have 2 halogens bonded to it that are geminal on the same carbon, and then another pair of geminal halogens over here, and those 2 pairs are vicinal to each other. So vicinal, geminal, tetrahalide. These reactions are very similar to what we saw with our alkenes, but the mechanism is different. And the mechanism is actually not full yet, and just other reactions I've mentioned in this chapter. A book does have some proposed mechanisms, some ones that are being researched, but there isn't anything that is fully known right now about these reactions. Our next reaction we're looking at is ozonolysis, and again we saw this one with our alkenes, and with our alkenes it would cut that double bond in half and give us ketones and aldehydes. With our triple bonds, we're going to cut that triple bond in half, and any of our internal carbons are going to become carboxylic acids. So we go from having 3 bonds to a carbon to 3 bonds to oxygen, 2 to that carbonyl, and then 1 to that alcohol, and all together it gives us a carboxylic acid. Now if our internal alkyne is symmetrical, meaning these R's are the same, then we'll end up with one product, but if those R's are different, if it's asymmetrical, then we'll end up with a mixture of carboxylic acid products. Notice our reagents here, we're adding ozone in step number 1 and water in step number 2. If we start with a terminal alkyne, our terminal carbon is going to turn into CO2. And this is a good thing because as we're doing this reaction, the CO2 is a gas, it's going to bubble away, leave us with one product and not a mixture of products. So it actually makes it easier for us to do this type of reaction. And our last reaction we're going to look at is an alkylation reaction. This might be the most important reaction in the chapter. And the reason for that is because we are going to create a new carbon-carbon bond. Most of the reactions we look at in organic chemistry are adding functional groups or removing functional groups. There's very few that actually change the carbon-carbon structure of our compound. So in this reaction, we need to start with a terminal alkyne. We have to have that hydrogen attached there. We're going to react it with NaNH2 in that first step. So remember, we can think of this as just NH2 minus. That NH2 minus is going to remove that hydrogen and create a carbanion. We'll look at the mechanism on the next slide. That carbanion is then going to react with an alkyl halide. This alkyl halide needs to be a methyl or primary alkyl halide. But what we're doing is an SN2 reaction. We're going to do a nucleophilic tag, and the loss of a leaving group, and as a result, we're going to create this new carbon-carbon bond. And it's a way for us to make our starting material larger. It's a way for us to start with small molecules and create larger ones. If you are doing this in a lab, small molecules are a lot cheaper. So this is a way to build something larger that might be more cost effective. If we start with ethine, so we have that terminal carbon hydrogen on each end, we can do the reaction twice, and we can add an R group to each of those carbons, creating a larger structure and still leaving that alkyne intact, which means that it can still go through all of the other reactions we've looked at. We haven't lost the reactivity of that functional group. So here's the mechanism. It's pretty short and sweet. We're starting with a proton transfer. So we're taking our base, grabbing onto that hydrogen acid. We're breaking that bond, leaving the electrons on that carbon as a carbanion. And then in the second step, we're using that carbanion as our nucleophile. We're doing a nucleophilic attack on our alkyl halide and carbon-carbon bond. So we're going to take a little practice break here. So we are going to look at alkyne reacting with a few different sets. We're going to start over here with our Cl2. We have a 5-carbon chain alkyne between carbons 1 and 2. So I'm just going to 1, 2, 4, and 5. And when I add 1 equivalent of my chlorine, I know that I'm going to add 1 chlorine each of my alkyne carbon. That triple bond becomes a double bond. And I drew this as a anti-addition, which is our major product, and the syn addition, same side of that double bond, so this would be my syn addition or my minor product. And then adding excess bromine, we are add 2 bromines I'm going to add 2 bromines to carbon number 2 and 2 bromines to carbon 1. Now neither one, don't really need to worry about which way we point those structures as we draw them. Going straight up, we are going to do an ozonolysis reaction. Carbon number 2 is going to become a carboxylic acid. 2, 3, 4, 5, and carbon is going to be CO2. So because this is a terminal alkyne, our internal carbon becomes. Now going in this direction, our N is going to create a carbanion iodide. We are at the 6th carbon. The numbering system doesn't quite make sense. The point of the numbers is to keep track of all of our carbons. So we have our 5 original carbons, and then we just attached on. And then if we do an ozonolysis reaction, now we have internal alkyne. We're going to cut that triple bond in half. So this is carbons 2, 3, 4, and 5. Carbon number 2 is going to become a carboxylic acid carbon, and I also have carbons 1 and we will get a second carboxylic acid of a different size. Let me put a little plus between those. So we have one more slide and one more topic to look at. The last section in this chapter is looking at multi-step synthesis, and really this is our last section in most of our chapters that we look at. And as we learn more reactions and we're trying to do a multi-step synthesis, there's really 2 questions that we should be focusing on, and the 2 questions are: does the carbon skeleton change? So does it become shorter or longer? And do the functional groups change? these are going to give us the pieces of information we need to then figure out which tools we need to utilize as we go through that functional group and carbon skeleton changes. Down at the bottom here, it's showing us essentially a summary of how to convert a single, double, and triple bonds from one another. Now, going from a single to a double bond is not something we've learned. It does say here that we'll learn it in chapter 10, but it gives us a couple strategies to make those transitions. So the last thing we're going to do in this video is look at a couple different multi-step synthesis reactions and talk about how to solve them. So we're starting with 3 carbons and we have a triple bond. So 3 carbons. What we are making 5 carbons and 2, and the bromines are syn to each other. So we need to find to add multiple carbons, 2 carbons to our chain, and then add some bromines. Well, one thing I also like to look at is, I did number this 1, 2, 3, 4, 5, but I think that these 2 carbons are those 2 carbons. And the reason for that, we can't react carbon number 3. We don't know how to react just an alkane carbon, a single bonded carbon, but we do know how to react triple bond carbons. And here is that the carbons with the bromines attached are those triple bond carbons. So that's to attach on carbons number 4 and 5. And we know how to do that. We know how to react this, and I'm going to react it with an ethyl group. And I'm going to number it 2, 3, 4, 5. 3 original carbons and then my 2 additional carbons. So my numbering matches my, and I've solved one of the problems. I have enough carbons. Now, the next step though is to add on those bromines. Now we know if we do 1 equivalent of bromine, we can add on our bromines to carbons 2 and 3. We also know that if we do that, we're going to get a mix of syn and anti-addition, and this only has the syn. So another way to do this would be to change this into our alkyne, from our alkyne to our alkenes first. So I'm going to use H and Lindlar's list. And I'm specifically using that one because it gives double bond. If I used our dissolving, it would give me a trans double bond, and I would end up with the opposite stereochemistry. And then my last, going back to chapter 8, we know that we can react our alkene with Br2, be a syn addition, and so we'll end up with our bromines syn to each other. So this ended up being a 3-step reaction. Let's look at our next one here. We have a carbon triple bond. We have a 5 carbon chain with an aldehyde attached to it. One where we think about working backwards. We know how to make aldehyde. We know that if we react our boron, and I like to use 9-BBN for this, if I react my N with hydrogen peroxide and hydroxide with a terminal alkyne, then I can create. So this is doing a retrosynthesis, so thinking of it from a backwards perspective. And so then the last thing is, how can we go from 2 to 5 carbons? Well, we're essentially going to do the same thing we did up here, but with a propyl group instead of just a 1 step. to increase that 3 more carbons, and in one our terminal alkyne to our aldehyde. All right, so I paused so that I could edit my last one, that I had made a mistake when I drew it and my product, so little cut in there. Last one, we're going to do the same thing. We're starting with 2 carbons with a bond. We are ending with 6 carbons, and that functional group on that is called an epoxide. So we're going to start. We know how to add on those 4 extra carbons. I'm going to react it with NaN2 and butyl bromide. So I have my 6 carbon chain there. 2 carbons 1 and 2 are my triple bond, and then I've added 4 extra carbons. Now to do that in chapter 8. Chapter 8 told us how to get our epoxide, and we can do that in a peroxy acid. So our most common one we use is MCPBA, but that means we do need to have our alkene first. So we have a couple options for that. We've already used hydrogen with catalyst, so I'm going to use our other option. I think I drew too many carbons. So now I have my 6 carbon chain. My triple bond has been reduced down to a double bond. And my last step, I'm using MCPA is our peroxy acid. So any peroxy acid will do, but MCPB is definitely the most common one that we see. So a little practice on how to do those multi-step syntheses using some past reactions and our new reactions. This is it for chapter 9.